Okay, in this tutorial, first of all, we would like to go through the previous knowledge, and the second part, it will be mainly about balancing equation and how to use mole concepts, and also, well, in the equation in order to find some unknown information. So first of all, the first topic is about relative isotopic mass. If you remember, in this world, there are a lot of elements. Take this as an example. Potassium is one of the elements, and we say that in this world, not all potassiums have the same mass. This is one kind of potassium atom. We call it potassium 39. Another one is also potassium ion, but potassium atom, but the mass is different. It is potassium 41. They are both potassium. However, one of them weighs 39, or sometimes you may say 39 units. The other one weighs 41. It is fatter, or it is more heavy. Okay, so we can define the mass of them are 39 and 41 respectively. And in short, we can say that the relative isotopic mass is the mass number of that particular isotope. Okay, so relative atomic mass is another concept. It is called the weighted average mass of all the naturally occurring isotopes of the elements. What's meant by a weighted average? Let's look at this picture. Suppose this is the picture of the real potassium atom. Suppose inside some potassium metal, we can obtain some of them 41 potassium, some of them potassium 39, and in this ratio, only very few of them is potassium 41. Say maybe 5% of them is 41. 95% are potassium 39. So how can we define the relative atomic mass? It is called the weighted average. So we can calculate in as follows. 39 times 95% plus 41 times 5%. So the weighted average we say is 39.1. Note that there is no units here. You can pay attention to this value. Actually, in this world, no single potassium atom weighs 39.1 units. However, we could simply take 39.1 to be the mass of each potassium atom. It is the average mass of potassium atom. I repeat, no single potassium weighs 39.1, but we can take the average mass is 39.1, and we call this relative atomic mass. We use this to represent the mass of each atom. Okay, next we'll go to the formula mass. Formula mass is something that can be based on the relative atomic mass that we just discussed. Okay, what is it? Is it this formula mass? No, of course, just kidding. Formula mass should be the sum of all the masses of every constituent species in a formula. First of all, you have to know what is called a formula. Unlike mathematical formula, formula in chemistry does not have an equal sign. For example, MgCO3, then we call it a formula. It's like a combination of some elements or like ions or molecules, something like that. Then we call it a formula. So how can we find the formula mass? Is that if we know every element's relative atomic mass, then we can calculate the formula mass by summing all the constituent species. So let's look at this example. 24.3 is magnesium, plus 12, it is carbon, plus 3 oxygen, so it is 16 times 3, and then we say that it is the formula mass, and in each MgCO3 unit, we say the mass is 84.3. It looks like in each this kind of units, then we say the mass is 84.3, and it is formula mass. Note that no units also for formula mass. Just like relative atomic mass, also no units. Remember, no units. Okay, next we talk about mole concept. It is a very important and very abstract concept that you must know. Okay, suppose I say Mr. Chill, that's me, is 165 tall. Do you know how tall I am? Am I 165 km tall? Or 165 meter tall? Or 165 cm tall? Because without units, actually there's no meaning at all. So I say there must be some units for a quantity to be concrete, or for a quantity to have its meaning. It must have units. However, just now we said that formula mass, relative atomic mass, they both do not have units. So how can we make them meaningful? Then it comes to the mole concept. Okay, suppose we really look at one single carbon atom. For this atom, scientists found out that the weight, the mass of it is 0.000000001993355 gram. Okay, just take it as granted. Okay, the next is two carbon atoms. How heavy is it? It's 0.000000398 something. Three carbon atoms, also a very small trivial value if you denote it in gram. So we say this is not very desirable because if every time I tell you how was the mass of some carbon atoms, I use gram, like how, for one single atom, two single atom, three single atoms, the number itself does not have many very good meaning. You may not even know after you see this number. So when it comes to mole, okay, scientists found out that in 12 gram of carbon, you know that every carbon atom is very light. So in 12 gram, there must be a lot of carbon atoms. So how many carbon atoms are there in 12 gram? And scientists use some methods to find out that, okay, in this certain amount of carbon 12 atoms, the amount equals to what? 1 mole. Scientists define this quantity, this amount, to be 1 mole. And what is 1 mole? It is 6.02 times 10 to the power 23. This number means how many carbon atoms add up together will be 12 grams of mass. So you see every single carbon atom is very light. So this very big amount of carbon atoms just add up to 12 grams only. And this is called 1 mole. Okay, after you know this mole, then even next time it is not carbon atom. If it is like oxygen, if it's 16 oxygen, then 1 mole of 16 oxygen will equal how many? It will equal 16 gram. Yeah, if next time, if it is 16 O inside here, then it will equal to what? 1 mole of 16O would equals to 16 gram. Okay, then I hope you know this mole has its meaning. This is the quantity, so that 12 carbon atoms equals to 12 gram, 16 oxygen equals to 16 gram. Okay, next. So we can say molar mass. We can define molar mass now. In fact, it does not have a very great difference in the meaning as formula mass, but I say the meaning itself is different. Okay, molar mass means the mass of 1 mole of a substance. Mass of 1 mole of a substance. So just now we say what is the molar mass of carbon atoms? It is 12 gram because 1 mole of carbon atoms would be 12 gram. Okay, yeah, like this. Okay, and we can conclude that the formula mass of carbon is 12. No units here, but the molar mass of carbon is 12 gram. You can see that the number itself are the same. The only difference is gram, because formula mass has no unit, and then 1 mole of it will equals to 12 gram. That is why it's so convenient to use 1 mole. Okay, so let's look at this example. Find the molar mass of MgO. Given that Mg equals 24.3, O equals to 16. Okay, first of all, of course, we have to find out the formula mass. There's no unit, 40.3, easy. And next, just add gram there, and then it is called molar mass. No need any calculation, just add gram there after you know the formula mass. Okay, so in short, suppose the formula mass of something is x, then the molar mass is x gram. Very easy to remember, just add gram, right? Very easy. Okay, so I suppose you know this. Then next, we'll go to this lesson's material, this balancing equation first. Let's do it some revision with it. Okay, so let's look at this equation. We say equation. On the left hand side, we say it is the reactant side, like the elements or molecules or ions here are being reacted to form some products. So on the right hand side, we say product sign. Okay, is this equation balanced? Obviously, you can see that it's not balanced. Look at the left-hand side, 2 oxygen there, and on the right-hand side, 1 oxygen. So we say that it is not balanced. So how can we balance it? It is later you will know it. I'm not going to go through this example again. Okay, let's look at example number 1 then. Iron 3 oxide is heated with carbon to produce iron metal and carbon dioxide, right? A chemical equation for this reaction. Okay, so whenever you're doing a balancing equation question, if you're only given a question like this, but not an equation already, then you have to identify what reactants and what products are. Okay, so first step is reactant side. There are what? Iron 3 oxide, carbon. For the product side, there is iron and carbon dioxide. Okay, so first, of course, you have to obtain the formula for all these. So now, if you are not sure about some formula, let's revise about these. So the first one is what? Iron 3 oxide. How to obtain this formula? Fe2O3. Of course, you have to remember that iron 3 is Fe3 plus. Oxygen is oxide ion is O2 minus. So by this crossing, you can find out Fe2O3. Then we say this is the formula for iron 3 oxide. I suppose many of you know it, so I skip it. Carbon, C, easy. Iron, Fe, easy also. Okay, finally, carbon dioxide is a very common product, so you should remember it. It must be CO2. In fact, dioxide, the prefix di means 2. There are 2 oxygen. Okay, after we obtain all these 4 formulas, then we can just write them into one equation. But now, of course, this is not balanced yet. So how can we balance this equation? So we have to look at which constituent species, or we say which entity, are not balanced yet. Okay, you can look at this equation and find that easily. Iron is not balanced yet. Okay, why I say iron is not balanced yet? Because iron 2 here, but only 1 iron over here, over the right side. And oxygen also not balanced yet. O3, O2. Okay, so our objective is to balance iron and balance oxygen. Okay, so the first method that I suggest is maybe we can try balance iron first. So on the left hand side, 2 iron. On the right hand side, 1 iron. So we can just add 2 here in order to balance iron. Okay, now iron has already been balanced. So in the next step, we should not alter this term and this term anymore. We should not alter these 2 terms anymore because they are already balanced for iron. So which one can we alter in order to balance oxygen? Okay, we can try to change this coefficients to become 3 over 2. 3 over 2. don't worry, it can be a fraction at this step. It can be 3/2, so that oxygen is now balanced now. Okay, now our carbon is not balanced yet, so we can fix our value here, 3/2 as well, to balance carbon. Okay, now because following the steps, iron, oxygen, carbon, so all of them should be balanced now. And but we cannot accept fraction in the final answer in the equation, so we can maintain the same mole ratio by multiplying 2 of multiplying 2 to all the terms. Then the ratios will still be the same. So we can multiply 2 becomes 2, multiplies 2 becomes 3, multiplies 2 here becomes 4, multiply 2 here becomes 3. So we say that it is the simplest ratio, simplest mole ratio, and is now the equation is done. Okay, as I say, there's method 1, there should also be method 2. Is balance oxygen first. Okay, if you can see that O3 here, O2 here, I hope you can be smart enough to see that actually we can together add 2 and 3, so that oxygen is now balanced. Add 2 here, 6 oxygen overall. On the right hand side, 3 times 2 also 6 oxygen overall. So now we say oxygen is balanced. Next, iron, of course. On the left hand side, how many iron? 4 iron. So we have 4 iron. Also carbon, 3 CO2 here, so we also have 3 C. Then we say it is now done. And of course, finally, we have to double check if there are still any unbalanced species. But of course, usually if you follow every step clearly, then it should be done perfectly. So yeah, just double check for safety. Okay, so I hope there's no questions. And we will move on to the next example, example number 2. Yeah, you are going to try to balance this equation. Okay, first of all, we have to identify what species are there. You may say Al, S, O, Ca, H. Yes, you may say there are 5 species altogether, and you are going to balance every one of them. However, for this particular case, I would suggest one maybe shortcut or one easier way is that since you see SO4 always occur in a group, SO4 occur in together, bind together. Also here, SO4 also bind together, so you may treat it as one entity or one species. For HOH, also it occurs in the same group as well. So we say there are 4 terms overall: Al, SO4, Ca, OH. Only for this case, not for all the cases. You have to identify that SO4 always occurring in together, OH always occurring together. Then you can use this method. We can treat these two as a whole, then it may ease our balancing. Okay, first step, of course, we can try to balance aluminium first. You may try others, but just my suggestion. You see aluminium is 2, so we add 2 as a coefficient here. Next, what do you suggest? I suggest 3, adding here, in order to balance which? OH. Note that just now for the first step there are 6 OH, 2 times 3, 2 times 3, 6 OH overall. So on the left hand side we also should fix the number so that there are 6 OH, 6 OH. Okay, next step now calcium is also not yet balanced, so we add 3 here in order to balance calcium. Finally, double check. Okay, and I suppose it's a perfect answer now. Every constituent species are balanced now. Okay, we move on to example number 3. For example number 3, it's like a very simple case, so I'll just do it very fast. First of all, you can see that aluminium but not balanced here. So maybe we can try to fix a 2 here. Oh, sorry. Let's move backward. Yeah, you can also fix aluminum, but I suggest maybe fixing oxygen first, maybe a smarter way. Just add 3O2 to balance oxygen first. Next one, just add 4 in order to balance aluminium. Okay, and then it's done. Sometimes you can see the order of balancing. I would suggest sometimes because aluminum itself is just a single element. There is no 2 here or no not combining with some others. Al is a single element, so it is the easiest for you to adjust the coefficient to match others. So as it is the easiest, so maybe we can put it as the final step. Now we can try to balance other things first, so that at the final step we can still just put in some number to adjust aluminium's amount easily. Since it is easy to adjust, we put it in the final step. So we do oxygen first and then do aluminium. It's just my suggestion. You can use other ways, still find the same answer. Okay, next would be after you know how to balance equation, and then I would say the next session is the most important because we are going to use equation and mole ratio. We are going to combine these two concepts together in order to find some very important information. So let's look at this equation first. 2Cu plus O2 and then it will make 2CuO. I want to emphasize on the meaning of this equation first. So let's look at this diagram. From the equation, we can tell what? We can tell one thing. If we have 2 Cu atom plus 1 oxygen molecule, 1 O2, and then you can have 2 CuO as the final product. This is the first thing that you can tell. 2 copper atom, 1 oxygen molecule, and you can find 2 CuO as a product. But it's not always the only case. This is also a possible case, right? If you have 4 Cu, 2 oxygen molecule, and then you can still find 4 CuO. By this equation, you can also tell this. The next is if you have 6 Cu, 3 O2, you can also have 6 CuO. Okay, what about this? If you have a lot of copper, a lot of oxygen, and then you have also a lot of CuO. Of course, to abstract the things, we say this amount is 2 mole of copper. This amount is 1 mole of oxygen molecules. This is 2 mole of copper oxide. It is still possible by this equation. This equation, in short, just specifies the mole ratio. We say the mole ratio is that copper to oxygen to copper oxide must be 2 to 1 to 2. If there's 2 mole, then 1 mole, then 2 mole. 4 mole, 2 mole, then 4 mole. 2.4 mole, 1.2 mole, 2.4 mole. Yeah, as long as the mole ratio are the same, we can still say this is a valid combination. 2.4 mole of copper add this amount of oxygen and you will still form 2.4 mole of CuO. Don't worry, since mole is a very big number, so it can be a decimal number here. 2.4 mole is still okay, as long as the ratio are kept, 2 to 1 to 2. Next one, even 3.18 mole, 1.59 mole, 3.18 mole are still okay because the mole ratios are the same. Okay, now I suppose you understand this. The chemical equation tells us one very important information is that the mole ratio can be deduced from the coefficient of the species. From the equation is 2 to 1 to 2. Then we can say this is the mole ratio of every reaction between Cu and O. Yeah. the mole ratio must be the same. Okay, so next we can look at example 4 using this concept. 7.29 gram magnesium ribbon. Okay, completely burned. The word completely is a keyword. Okay, it means all the magnesium has been reacted. That in the equation you can use this amount. This is the amount of magnesium reacted. Okay, to form what? Magnesium oxide. So what is the mass of the magnesium oxide formed? Of course, the first step is you have to write the chemical equation first, otherwise you cannot deduce the mole ratio. The chemical reactions equation is just like this, very easy. I suppose now you know how to write this equation. Okay, so we can tell the mole ratio between Mg and MgO is what? 2 to 2. 2 to 2. Okay, since all 7.29 gram of magnesium are reacted, so how many moles here can deduce how many moles of MgO? How many moles of MgO? So let's look at the number of moles of Mg. How can we find out that? 7.29 gram is the mass of it. And 24.3 is what? Relative atomic mass, or I should say a molar mass. 24.3 is molar mass here. Mass divided by molar mass, then we can obtain a number of moles. Okay, so from the equation, the mole ratio of Mg to MgO is what? 1 to 1. 1 to 1. So number of moles of MgO is also 0.3 mole. Also 0.3 mole because it's 1 to 1. So it is also 0.3 mole. This is the reason 2 to 2 same as 1 to 1, so it's 0.3 mole. Okay, so what is the mass of MgO formed? Is we know the number of moles, and then we have to multiply its molar mass. Note that this time the molar mass of MgO is not 24.3. MgO itself is 24.3 plus 16. You may argue that this is also the formula mass. Yes, you can just treat it as a formula mass, and then add gram, and it is molar mass. So finally, the answer is 12.09 gram. Remember, it is gram because it is supposed to be molar mass. Molar mass has gram as a unit. And obviously, for mass of MgO form must be a gram that you're familiar with. Okay, so let's move on. Before we talk about the last example, consider this case. We still have the same equation. We know that 2 to 1 to 2 are the ratio that if all of the elements are reacted. However, if in this case there are 2 copper atoms and a lot of oxygen. So how can you deduce how many products are formed? Should the products be determined by number of copper atoms or determined by number of oxygen? Okay, then it comes to the concept in excess and limiting reactant. Okay, in this case, as there are a lot of oxygen, there are too much oxygen. So just too much. Only part of them are reacted. So we say oxygen is in excess. And how many products are formed should not be dependent on the number of oxygen. It should be instead depending on copper, because there are only 2 copper. There cannot be 3 CuO formed. There cannot be 4 CuO formed. There must be at most 2 CuO formed only, because there are only 2 copper. Only 2 copper. So we say copper is a limiting reactant in the chemical reaction. If we calculate the mole ratio, we should not use O2 to calculate the mole ratio because O2 are too much. Even there are 10 moles of O2, we cannot say there are 20 moles of CuO because not all oxygen are reacted. So the products depend on limiting reactant. limiting reactant means the one that is less amount, less number of mole. Not exactly, not less number of mole after you adjust the mole ratio. Okay, let's look at example number 5. Where 4 moles of hydrochloric acid react with 72 grams of magnesium. First of all, of course, we have to write the chemical equation in order to find out the mass of the hydrogen produced. Okay, Mg plus 2HCl, like this. If you cannot get this equation, then very likely you will get a wrong answer. So you have to be very familiar with metal plus acid. What are the products that can be formed? You must be very familiar with this. So after you obtain the chemical equation, you can calculate the number of moles of Mg is 2.96 mole. Okay, 2.96 mole. Just now you see that how many moles of HCl? 4 mole, right? 4 mole. Okay, let me write it for you. Is 4 mole of HCl and 2.96 mole for Mg. 2.96 mole for Mg. Okay, so you see that they are not in the ratio of 1 to 2, so there must be one of them in excess and another one is the limiting reactant. So how can we determine which one is the limiting reactant? Okay, I will suggest one way. If you look at Mg 2.96 mole, in order to let all these 2.96 mole reacted, how many moles of HCl has to be used? Because it's 1 to 2 ratio, so in order to react all Mg, there should be 5.93 mole, 5.93 mole of HCl. Okay, there is some rounding error here, so it should be 5.93 instead of 5.92, but it doesn't matter much. 5.93 mole of HCl in order to undergo complete reaction of Mg. However, there is only 4 mole of HCl only. It requires 5.93, but there are only 4 HCl only. So which one is in excess in this time? We call Mg is in excess because not all of Mg can be reacted since there is only 4 mole. And we say HCl is the limiting reactant because we need 5.93, but there is only 4 mole. It means not enough to react to let all Mg reacted. So we say HCl is limiting reactant, Mg in excess. And if we are going to determine H2, which one should we use to find the mole ratio? Should we use limiting reactant or the one in excess? We should use the one limiting reactant, because if it is in excess, it means it's too much. Not all of them is reacted. So number of H2 should not be determined by in excess one. It should be limiting reactant. Okay. So what is the number of mole of H2? Is 2 to 1 ratio. So in the next slide we can tell number of moles of H2 is 4 times 1 over 2 because 2 to 1 ratio. 2 to 1 ratio. 2 mole of H2. Of course, finally we have to calculate the mass of it. The mass is just multiply relative atomic mass of hydrogen. For hydrogen is just 1. But H2, so 1 times 2. 2 mole times 1 times 2. And then we find 4 grams. So finally, there are 4 grams of hydrogen produced. Okay, I try to repeat once again. For this, since we calculate mole is 2.96 mole, HCl is 4 mole. So we first have to determine which one is limiting reactant, which one is in excess. And after the logic that I just discussed, Mg is the one in excess, HCl is the limiting reactant. So we use limiting reactant to determine H2, number of mole, or the number of mole of H2. So we calculate the 2 mole of H2 and then calculate the mass by number of mole times molar mass program. Okay, I wish it's clear. So for the assignment, please complete the remaining questions and submit notes in the next lesson. Thank you very much. If you have any questions, you may find Mr. Chiu at any time that you encounter him. Okay, thank you.